Titanium Welding, Part 1. Gary A. Pace, PE, CWI, Katy, Texas, April 2019. Our learning objectives in this module are we're going to talk about some basic information about titanium. Get a little bit of vocabulary down. We're not going to be experts at it by the time we're done, but we're going to have a pretty basic idea about some of the terminology um, in regards to titanium and titanium alloys. Um, Basic information and basic terminology, figure out what's good and what's bad for titanium, and just some general vocabulary. Get our feet wet before we take the plunge later on into welding of titanium. Okay, we're going to talk about titanium. We're going to talk about welding it. We're going to talk about the metallurgy a little bit, a couple of the different phases, crystal structures, all that kind of stuff. So to start with, those of you that don't know much about titanium, titanium's number 22 on the periodic table. It's above zirc, right next to vanadium. It's in that same row as potassium. And it's a pretty light metal. It's a little heavier than aluminum, which is on the atomic periodic table of elements. It's number 13. And it's a little lighter than iron is over there at 26. It's got good corrosion resistance to things like seawater. It's got a good strength to weight ratio. It handles pretty well, but it's expensive and it's kind of onerous to fabricate. It's not as forgiving as aluminum or iron are. And when I say iron, I mean the steels, the iron carbon materials. So we're going to kind of go off into a little conversation about titanium, different titanium alloys, pitfalls when welding titanium, etc. Titanium and titanium alloy desirable properties. Titanium and titanium alloys have a number of desirable properties, and when suitably combined, these properties make the metal the best material for a variety of service applications. These properties include excellent fatigue resistance, good notch toughness, stability over wide temperature range, low coefficient of thermal expansion, low thermal conductivity, outstanding corrosion characteristics for some of the most troublesome industrial chemicals, excellent resistance to erosion and cavitation from high velocity fluid flow, no scaling below 800 degrees F, although discoloration of the metal may occur, inert in electrochemical operations when charged as an anode in electrochemical circuit. These properties are important in a variety of applications, including airframes, jet engines, aerospace equipment, chemical or processing equipment, and electroplating equipment. Whether manufactured from bar, plate, sheet, or forgings, some type of joining operation often is required to assemble components or subassemblies as a step in completing the final product. So you can see here there's a lot of really good things about titanium. Good notch toughness, good fatigue resistance, low coefficient of thermal expansion. So when you get it hot, it doesn't expand a lot, or if you get it cold, it doesn't contract very much. It's got really good corrosion characteristics for some really bad industrial chemicals. So you can see why titanium would be a material that engineers would choose for a lot of different applications. Airframes, aerospace, chemical processing, a lot of different directions we can go with this. Important features of titanium alloys. Important features of titanium alloys that must be considered to successfully join this highly reactive material are the extreme sensitivity of titanium to embrittlement by small amounts of some impurities, the very high reactivity of titanium not only at welding temperatures, but at temperatures as low as 1200 degrees F, the effects of heating and cooling cycles involved in joining operations on the mechanical properties of the alloys, the inherently brittle structures which are almost always formed when titanium is joined to other metals, the specific titanium alloy composition to be used, and the sensitivity of titanium and titanium alloys to embrittlement imposes limitations on the joining processes that may be used. Small amounts of carbon, oxygen, nitrogen, or hydrogen impair ductility and toughness of titanium joints. So this is telling us all the red flags we got to worry about. The big ones are down here at the bottom, in my mind. Carbon, oxygen, nitrogen, or hydrogen. If you get it into the weld puddle, you got to start all over. That weld is bad. So we really need to watch those when we're welding titanium, and I'll probably get more into those interstitial elements and when we talk about welding in the next video. So, and above 1200 degrees F, titanium is very reactive. Every now and then I think it's out in Oregon, there's a place that manufactures titanium. They'll have some kind of fire or explosion. I had a professor that used to deal with titanium. He was a guru of the stuff back in the day in the 60s. But anyways, he said it's not if the titanium catches on fire, it's when the titanium catches on fire, if you're processing it, machining it, or whatever. So it's very reactive. Also, when I was down in Nevada, I forget the mine, outside of Winnemucca, they use a lot of titanium because they process this gold ore that's a sulfide, and I think they cook it and turn it into an oxide. So it's in a pretty corrosive environment because there's a lot of sulfur in there, obviously sulfides. So, but every now and then they'd have a fire. I think they were using this was back in the early or mid 90s, and every now and then these pieces of tubing that were sparging tubing would catch on fire or something. I just heard bits and pieces of it when I was in the bar, but the stuff would catch on fire and they'd put one of these pressure vessels through the side of the building or something. So, but anyways, it is a miracle material, but there are some things that could go wrong when welding titanium and dealing with titanium. So you need to be cognizant that there's some special things that you need to do when dealing with this material. Titanium. Okay, properties. Pure titanium has a tensile strength of 100,000 psi, a Brinell hardness number of 200, specific gravity of 4.5, a melting point of 3,300 degrees F, and good corrosion resistance. Alloyed titanium has a Brinell hardness of 340, a tensile strength of 150 psi, and a high strength to weight ratio, twice that of aluminum alloys at 400 degrees F. Appearance test. Titanium is soft, shiny, silvery white metal that burns in air and is the only element that burns in nitrogen. Titanium alloys look like steel and can be distinguished from steel by a copper sulfate solution. The solution will not react with titanium but will leave a coating of copper on the steel. Interesting stuff to know. I didn't realize that it is the only element that burns in nitrogen, but good to know. Titanium. Titanium is used as an alloying agent for aluminum, copper, magnesium, steel, nickel, and other metals. It is also used in making powder for pyrotechnics and in manufacture of turbine blades, aircraft firewalls, engine nacelles, frame assemblies, ammunition tracks, mortar base plates. Capabilities. Titanium can be machined at low and fast speeds, formed spot and seam welds, and fusion welded with an inert gas process such as gas tungsten arc welding. Limitation. Titanium has low impact strength, seizing tendencies, and low creep strength at elevated temperatures, above 800 degrees Fahrenheit. It can be cast into simple shapes only. Well, titanium is a pretty good material. It's pretty corrosion resistant. It's light and it's strong. It's got a lot of capabilities. So it's a little lighter than steel and a little heavier than aluminum, and it's pretty tricky to weld. But it's a good material if you need strength and weight. you know, a lightweight material with a good strength. It's a good quality material that can be used in a lot of different ways. So what would any conversation about metals be without talking about crystal structures, right? Everybody's favorite part of these talks. So at room temperature, titanium, pure titanium, is a hexagonal close-packed material. And then as you heat it up, it's going to go through an allotropic phase transformation, and it's going to go from hexagonal close-packed, which is outlined in the red there, and it's going to transform into body-centered cubic. We all remember body-centered cubic because that's what iron is at room temperature. So this titanium goes from hexagonal close pack to body-centered cubic at a transformation temperature. So this is something we need to keep in mind, that there's a couple of different crystalline structures involved in titanium alloys. So we've got four main categories of titanium alloys. We've got alpha alloys, near alpha alloys, alpha and beta alloys, and beta and near beta alloys. And they're going to have different crystalline structures. The alpha phase, and this is the room temperature crystal structure of titanium, is hexagonal close packed, or also known as the alpha phase. So you can see over here what the hexagonal close packed unit looks like. The little atoms are arranged in an HCP arrangement. So when we're talking about titanium, we're talking about titanium alloys. Just like when you say steel, there's a lot of different steel alloys. So there isn't just titanium. There's a lot of different grades of titanium, and a lot of different, like four main varieties, I guess it would be. Well, one of the phases is the alpha phase. So if we want the alpha phase to be stabilized, we can stabilize that with these alloying elements: aluminum, carbon, oxygen, and nitrogen. For the most part, we use aluminum if we're going to stabilize titanium in the alpha phase, because if we try and use carbon, oxygen, or nitrogen, we're going to end up with too much of it in there. Those are interstitials. Bad things are going to happen. So generally, if we're going to do phase stabilization in the alpha phase, we're going to use aluminum as our alloying element. Titanium's got a body-centered cubic phase, which we'll touch base on here in a second. But it does have, when we talk about the beta phase, this is what we're talking about. We're talking about titanium that is in a body-centered cubic form. This is, as you can see from a crystalline structure, this is completely different than the hexagonal close pack of the alpha phase. So here's our list of beta phase stabilizers. These are alloys that we can use to stabilize titanium in the body-centered cubic form. We've got chromium, niobium, copper, iron, manganese, nickel, molybdenum, tungsten, and vanadium. So I think the big one here is probably going to be vanadium. You'll see a lot of aluminum vanadium kind of alloys, and these are, we'll get into that later, but a lot of times you'll see aluminum vanadium. So I think those are in the alpha beta phases, but these are the beta phase stabilizers. Titanium is like iron in the respect that it will go through an allotropic transformation, a phase transformation, at about 890 degrees C or 1634 degrees Fahrenheit. Titanium undergoes an allotropic phase transformation to a body-centered beta phase, which remains stable to the melting temperature. So you can see that unlike iron, which goes from body-centered cubic to face-centered cubic, titanium goes from a hexagonal close pack to a body-centered cubic crystalline structure. Alpha beta alloys. The mechanical properties and ductility of alpha-beta alloys can be affected greatly by heat treatment. The response of these alloys to heat treatment depends on the exact alloy content. Therefore, very few generalized statements about weldability of alpha-beta alloys can be made. Welding or brazing these alloys may significantly change the strength, ductility, and toughness as a result of the thermal cycle exposure during joining. So when you start doing your research into welding of titanium alloys, you can't just approach it as, yes, it's titanium, we're going to weld it this way. You need to find out the specific alloy and also the type of alloy. And you'll go from there, because as this says, there's very few generalized statements about the weldability of alpha-beta alloys. There's no one size fits all. So you really need to do your research when you're digging into doing any kind of fabrication using titanium alloys. Interstitial elements, carbon, nitrogen, and oxygen, all behave in about the same way in titanium. Small amounts of these elements can cause significant embrittlement of titanium welds. The effect of these elements on weld ductility and toughness are both progressive and additive. During joining of titanium, contamination by carbon, oxygen, hydrogen, and nitrogen must be constantly guarded against. So if you ever set up and you're going to weld titanium, it's a constant battle. This is not like welding on farm equipment. You need a clean room. You need very little air movement. You need welders that are just very meticulous, that really approach their job in a serious manner, because if you do anything wrong in regards to hydrogen, nitrogen, carbon, or oxygen, you're going to have problems and you're going to have to redo the welds. This can't be stressed enough. So we call these elements interstitial elements because they take up an interstitial space in between the titanium atoms. And as it says here, these are both progressive and additive. So this stuff builds up. You might get away with it once, but it's progressive and additive. So can't be stressed enough how bad the interstitials are in titanium fabrication utilizing welding. General. Titanium has a high affinity for oxygen and other gases at elevated temperatures, and for this reason cannot be welded with any process that utilizes fluxes, or where heated metal is exposed to the atmosphere. Minor amounts of these impurities can cause titanium to become brittle. So hydrogen, carbon, nitrogen, oxygen, all bad things in the titanium world. This is why we really need to talk about cleanliness later on, and purity, and things like fingerprints can just absolutely mess a weld up. So just remember that carbon, oxygen, nitrogen, bad. Can really mess up a titanium weld. We're trying to keep those things from contaminating our weld pool and or the base material at an elevated temperature. Some more general information. Titanium has the characteristic known as the ductile brittle transition. This refers to a temperature at which the metal breaks in a brittle manner rather than a ductile fashion. The recrystallization of the metal during welding can raise the transition temperature. Contamination during the high temperature period and impurities can raise the transition temperature period, and impurities can raise the transition temperature so that the material is brittle at room temperatures. If contamination occurs so that the transition temperature is raised sufficiently, it will make the welding worthless. Gas contamination can occur at temperatures below the melting point of the metal. These temperatures range from 700 degrees F up to 1,000 degrees F. So this is telling us that our friends oxygen, nitrogen, hydrogen, and carbon can absolutely destroy a weld, and it'll also cause our ductile to brittle transition temperature to go from something very low up to something at room temperature, where the weld is going to shatter like glass because it's acting in a brittle flat fashion and not a ductile fashion. Here's what a ductile to brittle transition temperature curve looks like. You see these with carbon steel. You know, your garden variety carbon steel, that transition temperature, the dotted line that goes in the vertical direction, that transition temperature is roughly freezing of water, about 32 degrees F, 0 degrees C. So anything above that, the steel's going to act in a ductile fashion. But it plunges down and you get closer to 0 degrees F, and let's say minus 10 or 15 degrees C, it's going to be a more brittle material and it's going to shatter. That's why a lot of times when you manufacture something, you need to know where the part is headed. You know, something that would act in a ductile fashion in Houston, Texas, or out in the Arizona desert, you ship it up to British Columbia, northern British Columbia, or the tar sands up north in Alberta. Those things are going to shatter like glass in the month of December when it's 40 degrees F, 40 degrees C. You know, the material's gone through a ductile to brittle transition temperature. So that's why a lot of times they'll add, for steel, they'll add alloying elements in there to shift the ductile to brittle transition temperature to the left. And for titanium, what they're saying is if you contaminate the weld, you're shifting that ductile to brittle transition temperature from where it would be on the left way to the right, and it'll shatter at room temperature. It'll go through that, it'll behave in a brittle fashion and not a ductile fashion. At room temperature, titanium has an impervious oxide coating that resists further reaction with air. The oxide coating melts at temperatures considerably higher than the melting point of the base metal and creates problems. The oxidized coating may enter molten weld metal and create discontinuities, which greatly reduce the strength and ductility of the weld. So what this is telling us is you got to get that oxide coating off of the base material before you start welding. So a lot of times you'll use a grinder or a flapper wheel or some kind of excavation device to remove that material before you start welding. Or sometimes they'll use an acidic pickling where you'll stick the titanium in an acid solution and it'll chew that oxide coating off and you'll just have the base metal. Then you'll make your weld really quick, not super quick, but you've got some time before that oxide coating reforms. We covered the basic information about titanium. We talked about crystalline structures, body-centered cubic, hexagonal close pack. We talked about interstitial elements, some basic information about titanium. We talked about the need to keep it clean, cleanliness, just some general information about titanium before we talk about how we're going to weld the titanium. Just some general information was covered. All right, here's a list of sources that I used. Welding of titanium and annotated bibliography. Most of this stuff's in the public space other than the AWS stuff. AWS D10.6, recommended practice for gas tungsten arc welding of titanium piping and tubing. Welding procedures for titanium and titanium alloys, NASA Technical Memorandum, TMX 53432 from October 1965. The inert gas shielded metal arc welding of titanium, Oak Ridge National Laboratory, ORNL-2612, and then TC9-237, Welding Theory and Application, U.S. Army. And I also dug through the American Welding Society Welding Handbook. They've got a pretty good chapter in the Welding Handbook, Volume 5, Materials and Applications, Part 2, in the 9th edition. They've got a pretty strong, section in there on titanium, the titanium alloys, and all that pertains to welding titanium and how to handle it and the different processes you can use to weld titanium. Questions, comments, or whatever. My name's Gary Pace. I'm a professional engineer, welding engineer, certified weld inspector. I'm out of Katy, Texas. There's my email address and my website. Feel free to drop me a line if you have questions or whatever. Want to chat about welding related or materials, or maybe you've got an idea on something I need to cover in a future episode. All right, take care. GP out.